Okay. Hi, everyone. I'm Yufan. Today I'm going to present the VISTA-3D. Um, I'm going to present a foundation model for 3D segmentation, the VISTA-3D. The name is called Versatile Imaging Segmentation and Annotation. And this is a teamwork from the whole DLMAT team. This is our team members. And so for the model, we're going to talk about the overview of VISTA-3D, and then the model performance, the method details, and the NVIDIA 3D NIM demo. So the key point for VISTA-3D, the goal is to support the whole 3D segmentation workflow out of box. So VISTA-3D is the best existing CT foundation model that support both 3D automatic and interactive segmentation with state-of-the-art accuracy. So the first is we support the state-of-the-art out-of-box automatic segmentation for 3D CT. We support a diverse classes, like 127 classes, including 7 types of tumors and lesions. And the model is trained on 12,000 CT scans on 25 public data sets to give this model a strong generalizability on CT scans. The second part for this model is the interactive segmentation experience. So unlike the SAM, which is developed based on 2D, we developed the 3D interactive segmentation model. The VISTA-3D, the same model can do both automatic and interactive. And it's in 3D space, so it's efficient 3D interactive segmentation. And users can provide clicks to segment those 127 classes or refine the automatic segmentations with a few clicks. Besides that, we also have the zero-shot capabilities. And if user provide clicks for unseen structures, the VISTA-3D can also help the annotation of those unseen structures. Third, the whole model and the code is open source. All the model weights, training, evaluation, and data set curation codes are open source. And we provided the NVIDIA NIM service demo and OHIP plugins for trying this model. The paper, code, and demo can be found in the 3 links. So the first we'll go through the model overview. This figure is the network structure of the VISTA-3D. So we first have a 3D encoder, which is based on 3D convolutions. We take input image batch. The whole pipeline is based on the traditional sliding window inference, which gives the best performance in 3D. And we have 2 3D decoders. This is 2, one for the automatic segmentation, and the other one is for the interactive. And we have AutoHead. This AutoHead takes user prompt. So user input, like you can say liver spleen, and the model will segment the liver spleen. This is the automatic results. You don't need to provide any click points when you just tell the model segment liver spleen. The other branch takes the user click points. User directly click in the 3D space, and the point head accepts those point clicks, and it will generate the 3D segmentation results. And these two outputs, they are merged with a sophisticated post-processing algorithm. And this is the model architecture of the VISTA-3D. And so when you use this model, we provide a workflow. So if user want to segment a class called user class, and so if user class is inside this 127 supported classes, you directly tell the model class prompt equals user class to VISTA-3D, and the model will output the automatic segmentation for the whole volume. And if the automatic results has some error, of course, for every algorithm is not perfect, you can correct those error by adding some point clips. And also user can directly use the click point to segment the user class. This is the first case. That's the user class is inside this supported class. For the other case, if the user class is outside of those 127 supported class, we call this the zero-shot mode. And the zero-shot mode is only supported by this interactive branch. So user need to create a new target called user class, and they use the point clicks to do a zero-shot segmentation. And when you annotated a few slices, a few scans, you can fine-tune the VISTA-3D with those few annotated examples. We showed the results in the later section, and the user can fine-tune the model and do this automatic segmentation. So here is the results of all VISTA-3D, and we compare with the state-of-the-art supervised training pipeline. I think NUNet and Allo3DSec, the people is familiar with these two. They're the widely adapted supervised methods. They train on each data set separately. So for all those data sets, we train each model for each data set and get the results here. And also we train another very famous model called Toast Annotator. It's also publicly available. So we directly apply the Toast Annotator out of the box. Also, SAM and SAM2 based model is also very famous and popular, but based on our experiments and the benchmarks, those 2D based methods, they are still far away from the state-of-the-art results in 3D, comparing with those 3D backbones. And here we benchmarked on those held out test sets on those data sets. And the Allo3DSec and the NUNet are trained on each data set independently. And so we have all those models for each method. And so the VISTA-3D auto is the automatic segmentation from the automatic branch. And the VISTA-3D point means one-click points for one organ. And we got the results in this line. And the VISTA-3D auto plus point means we do automatic segmentation on these organs, and we add one-click points to either on the arrow regions, whether it's false positive or false negative, we just add 1 point to fix those arrows. And this is the final results. So we see this VISTA-3D already achieved the state-of-the-art or comparable results with those models. And what we noticed, VISTA-3D is using out-of-box for all those data sets, but NUNet is trained for each data set. Each data set has an independent NUNet, so it's quite different. Also, for the total annotator results, you see this. These results are much higher because this data set is curated using NUNet, and total annotator is used to generate the ground truth for total annotator. So we put a star here. So VISTA-3D has a pretty high number, 89 for auto segmentation, which means it's almost reached or comparable performance with the state-of-the-art. And when you use point or correct auto results, you can achieve even better results. This is for the 127 supported class. So here's the qualitative results. We compare, we don't have quantitative results for this because we don't have ground truth. So we brought in a monkey data. And it's quite different as human body, but we directly apply the VISTA-3D and the total segmentator to this NIH monkey data. And we clearly show that the VISTA-3D has better generalizability to those data from different sources. And here we further benchmark the zero-shot interactive results. We obtained a public mouse data set. So the mouse, you see, this is quite different as a human body. And if you directly apply the out-of-box toast annotator or VISTA-3D auto branch, it's not going to work because the resolution, the whole structure is quite different. You won't get a good automatic segmentation results for those four structures, the lung, the heart, and the spinal cord. So this requires the model to have some zero-shot ability. So here we compare with the SAM-based method that claim to have zero-shot ability. The first is the MATSAM. MATSAM is 2D methods. We need to simulate and also supporting the bounding box. The other is SACVOL, which is similar doing the point clicks in the 3D space. So this is the four results, four graph for those four organs. The x-axis is the annotation efforts. We call the number of user click points. A bounding box is considered as 2 points. And this is the die score average over the whole test set. So the green line is the VISTA-3D. So you see at the beginning, when you have 1 or 2 click points, it's not. But when you increase to 10 points, it's going to give you a high score. And this is the MATSAM. MATSAM also achieved good results, but it requires much more annotation effort because it's based on 2D bounding box. So you have to annotate each slice one by one. But VISTA-3D is giving you results directly on 3D space. And the dashed line, this is another variation. We train the model without using the super voxel. We will introduce this in the later sections. So this shows that our method development gives the VISTA-3D a strong zero-shot capabilities, and it's indeed reducing the annotation effort for unseen structures. Also, this is other examples for the tumors. This is for the adrenal tumors, hepat tumors, and the kidney tumor. Here is the green line is the VISTA-3D. And this is the crossing point. It means using the same annotation effort, we achieve this level of accuracy. And yep, this is the graph for the zero-shot interactive results. The last part is when user annotated a few unseen organs, we still don't want to use interactive because that takes human effort. What we ultimately want is some automatic segmentation models. So we can use those annotated examples to fine-tune the VISTA-3D. And in this case, this is the number of training cases we use to fine-tune the VISTA-3D auto part. And this is, we can see 89 is the total training data for this data set. And we can also compare with all the VSEG and UNet and TOS annotator. And get the results. So we see that with only one annotated samples, those models trained from scratch cannot achieve a usable performance. TOS annotator is the same. We fine-tuned TOS annotator with one using the NUNet pipeline, so still is not giving you good results. But VISTA-3D, even with one case, it reaches 0.92. So it seems. But another trend we see when you use the whole data set, full data set, those results getting closer. So I think for fine-tuning purposes, VISTA-3D showed obvious advantage in a few-shot setting. We also compare on Word dataset. So the Word has several organs that was not in that supported class list, and we see the similar trend. When you have few annotated examples, those pre-trained models, not starting from scratch. If you have a pre-trained model, it's going to give you a heads up when you have fewer annotated examples. And in the end, it's achieving similar performance. But still, it's giving you better results than the NUNet if you look at this, the same here. This is for fine-tuning. And here we go into the technology details. The first part is to curate this huge data set for training. And a lot of people already did similar things. They curate a large data set by collecting all the public data sets. We did the same thing. We collected 21 partially labeled data set with ground truths. This is those publicly available CT data set. And we also curated some unlabeled data set from NLST like TCIA. We have in total 12,000 scans. And we generate pseudo labels with 117 classes using the TOS annotator model. We use this out of box to generate the pseudo labels for those unlabeled data set. Also for everything, because those data set, they're a partial label. So we generate those pseudo labels for all the data we have. And we use all the pseudo labels and the partial labeled from manual annotators. We use them all together to train the model. That's giving you the best performance on those supported class. We mean like, and for zero shot, if you train using those data, it's not going to give you a zero shot ability. And to achieve some certain kind of zero shot ability, we decided to distill the information from the SAM pre-trained checkpoint. So So what we did is for all those 25 data sets, we generated a 3-view SAM-based supervoxel as the whole volume segmentation. So you see, this is the results from the SAM's pre-train checkpoint. We use a 3D supervoxel to generate those pseudo labels, and after so exactly what we did is for each view we use them to extract 2D features, stack them to 3D, and we sum up all stacked 3D features and perform a supervoxel algorithm, a slick algorithm, and get those pseudo labels. And you see this gives you more. The SAM is learning a lot about the boundary, and training on this kind of supervoxel will help the VISTA-3D to learn more about the unseen boundaries. And this is some certain way to distill the information from those pre-trained 2D backbones. And from the zero-shot result, we see without training on those supervoxels, the VISTA-3D is not giving you enough zero-shot ability for unseen classes. But once you train on those data, it's improving a lot the zero-shot capabilities. So the training recipe, in order to achieve state of art for all those 127 classes, you have to solve those long tail problems, the class imbalance problems, also the resolution problems. So first we train, also we need to use the same model to achieve state of art, both in interactive and automatic. So it's a headache. And we split the whole training process into 4 stage. The first, we train the point branch. We only train this branch. The encoder, lower decoder, and the point head. We train this part with 25 data sets using those partial label, ground truth, pseudo label, and the supervoxel. And we randomly and iteratively sample points from ground truth and supervoxel. This intuition is to train a strong encoder that has a basic understanding of what a medical boundary is and what the 3D boundary is. And this step will result in a state-of-art interactive model. After training this, we will have problems because there are not enough tumor data set. The class imbalance is big. So we fine-tune the point branch with tumor data set to solve this data imbalance issue. After finishing this interactive part, we freeze the encoder and train this olive branch, this upper part. And we only used pseudo labels and the labeled ground truths. The supervoxel was not used in this part because the supervoxel doesn't contain any class-related information. The last step is to improve the underrepresented class, like the tumors, vessels. We fine-tune this olive branch with tumor data together with the synthetic data from Macy. So we use Macy to synthesis a lot of tumor data set and fine-tuned with both the synthesized data and the ground truth to improve the tumor results. This is the 4th stage for training this model. And the last, we provide a NIM demo to play with this model. So first, if you look at this demo page, you load the upper body CT and you can click segment everything. So it's going to give you like give you all the segmentation classes, the model support. It's the usage is just the same as total segmentator. The total segmentator support 117. Our model support 127. So, and when you click, it's going to give you those everything results. Besides that, you can specify which organ you want to segment. So it's going to cost a lesser memory usage and it's faster because it's promptable. If you only care a certain organ, you can select exactly what organ you want. Also, we can see this has some false negative. You can click some points, and it's going to fix. Yeah, you see this before it has some false negative. Now, if you add some click points, it's going to fix that for you. So this is what we say the interactive editing, refining the automatic results. The last, if you want to add some class that's never supported or unknown classes, for example, some error in the column, in the abdominal regions, you click some points and click run. And it's going to give you the segmentation result directly in 3D space. You see, we don't have this in our training data. It's completely zero shot. Yep, that's the demo. Everyone can try this demo online. So the last part is the limitations. Currently, the model is only supporting the CT images because our goal was to first develop some state of the art for one modality, and we expanded to more modalities. And we trained the model on a fixed 1.5 millimeter. So the entire point clip performance on very small structure may have some unsatisfactory results because we limit the resolutions. The second is some state out-of-box tumor tests, like the pancreas tumor, still have a gap with the task-specific models. The generalizability of tumor segmentation need further improvement. And we're developing the next version of VISTA to support more modalities. We already curated a large collection of MRI, and we will enable support the MRI in our next version. Also, we're finding more effective ways to improve the zero-shot ability. And also, the ongoing research include like unifying the 2D, 3D segmentation.